In this video, we are going to use derivatives to solve applied optimization problems in several different fields. So when we look at optimization, we have a constraint function. This is a condition that must be met. And then we have the other equation or function, which is the objective function, the one that we want to maximize or minimize. If we take a look at this first example here, that all negative real numbers x and y between 0 and 20 with the property that x plus y is equal to 20 and the pairs of which the numbers have the largest product. So in this case, the constraint is they have to add up to 20, and the thing that we want to maximize is their product, x times y, if x being one of the numbers, y being the other number. Here you can see, here is the constraint, they all have to add up to 20, and the objective function is their product have to be the largest value we can get. So what we do is we say, well, let's take the derivative of the objective function. In this case, we called it p. And notice we have two equations. We have x and y is equal to p and y is equal to 20 minus x. And what we did to get this is we just solved for y. This allows us to put the one equation as a substitution into the other equation before we take its derivative. So notice that we replaced y, and you could have done it with x, but in this case we replaced y with an expression in terms of x. And we get 20x minus x squared, and now we take its derivative and we solve. These are our critical points. If we want to make a connection, these are our critical points. So we get x is equal to 10. Well, if x is equal to 10, y is equal to 10. And so we know that we have two numbers. If x and y are both 10, then its largest output value that we're going to get when we multiply them will be 100. So when we are doing optimization problems, what we're going to want to do is we want to figure out what variables we're going to need to introduce. So we will label our variables. Now what we didn't do up above is we didn't say x is one number and y is the other, but we should have. Draw a figure if it makes sense to do so and label all your variables. Determine which quantities need to be maximized or minimized. So in other words, we're going to figure out what it is that we want to max or min and the range in which these values will make sense. We're going to write a formula to be maximized, so we're going to find our objective function as well as our constraining function. We're going to find any kind of relationships that are happening between the variables, whether independent or dependent. We're going to identify the domain, and that is, of course, up here when we determine the quantity we maximize and the range of values. That's our domain of values. That makes sense. We're going to find the maximum minimums, and the way that we do that is finding our critical points. So we're going to do derivatives. In our first example here, a rancher has 400 feet of fencing to construct a large rectangular corral. Now, we would have actually seen this for the first time in our Pre-Calculus 1 class. One side of the corral will be formed by a barn and requires no fence. So here's the barn that requires no fence. And we need to have three smaller, but they have to be equal rectangles for the other corrals. We need to figure out the dimensions of the corral that will maximize the total enclosed area. Notice the way that this is set up is that we drew a picture. We have these x's as the sides vertically, and we have y being the side horizontally. This is not the only way in which we can set this up. And what I mean by that is we could have called these y, and then we could have called each individual one here x. It doesn't really matter as long as you know what it is and you label them so that I know what it is. So in this case, I'm going to let x equal the sides perpendicular to the barn. And then, that should be barn, not barren, barn. And then y here, y is equal to the side parallel to the barn. I don't know why I'm going wild and crazy with the E's, just barn, B-A-R-N. There we go. Okay. And I can also do it by showing it with the picture. The thing I'm being constrained is that I have a total of 400 feet. That's the total amount of fencing that I have. So I know the way that I set this up is I have 4 x's, 1, 2, 3, 4. These are the sides that are perpendicular to the barn. I have 4 of those. I have one long y. So I have 4x plus y is equal to 400. Again, I could have wrote each one of these as y, and that would have changed this to 3y. So it had 3 y's. It doesn't really matter. It will work out no matter which way you do it. Now, if I want to then figure out what are my values for x and y that maximize the area, that P, or in this case I'll use A is equal to x multiplied by y. I will use my constraining function here to solve for one of the 2 variables and plug into my area one, the one that I actually want to optimize. So I'm going to solve for y. So y is equal to 400 minus 4x. So my area as a function of x now is going to be x multiplied by 400 minus 4x. So a of x is going to be equal to 400x minus 4x squared. Now I'm ready to take the derivative of this to find my critical points, a prime of x. This is going to be 400 minus, and then I'll have 16x. So I have 16x is equal to 400, and x is equal to 400 divided by 16. And not without, I don't have a calculator here, so I know that 4 will divide each one, so it'll be 10 over 4. And so that is going to give me, if I have 10 over 4, I'm going to have 5 over 2. So I end up, or excuse me, that should be 100 over 4. That'd be 50 over 2. That's what happens when I don't have my calculator with me. So I end up with 25. So my x value is 25, and then I would just put that into here, go back to this one, and I have 4 times the 25 plus y is equal to 400. 4 times 25 is 100, and so I get y is 300. And that will maximize my area. Provided, of course, I did my math all correct. So when you are trying to find the maximization of an optimization, do you need to check the derivatives around the critical points? Well, if we were in the land of graphing, yeah, we probably should. And if we're not in the land of graphing, we probably should anyways, just to make sure that we actually truly have found a max. Well, in this case, for this example I just did, I only had one critical point. And not only did I only have one critical point, I happen to know this is a quadratic shape because my power is 2. My leading coefficient is negative, and we know from our previous graphing, if I were to take the limit of this, that I would be going down, the function would be going decreasing on the left side of the vertex and decreasing on the right side of the vertex. So for this one, I didn't really need to do the checking on either side because I know this is a parabolic shape which will be opening down, which means I'm guaranteed a maxima. So I didn't have to on that one just because it's a quadratic. Now if it has a higher power or if it's not a quadratic, then I probably should consider checking the signs of the derivative on either side or doing the second derivative test. The endpoints, do we have to check the endpoints for optimizations? And sometimes, because we don't know whether or not the endpoints will actually produce the largest or the smallest, and these are absolutes that we are usually looking for, so we should check the endpoints. And this is some true and falses. True or false for every continuous non-constant function on a closed interval. Finite domain, there exists at least one x that minimizes or maximizes the function, and this goes back to, and I'm not going to answer this for you, or this following one for you, because this goes back to making connections to our extreme value theorem and our Rolle's theorem. So these are the things that we learned in previous sections. So if you're not sure, go look those up in the previous sections by definition, whether or not these are true or false. Okay, so here's some examples in which we are going to do some optimization. of all the rectangles with a perimeter of 10, which one has the maximum area? Now, so what we're going to do then, I like to draw a quick little picture. I have X, I have Y, and I don't have to label them other than X and Y. The perimeter is 2X plus 2Y has to equal 10. My area is going to be equal to X multiplied by Y. And once again, this is my constraining function. This is the function I will optimize. Put it all in one variable, solve for y this time because we can, and so we get y is equal to 5 minus x. So a of y is going to be, I was going to solve for x this time. Oh, okay, well, I'll solve for x this time. So x is equal to 5 minus y. So we have y, 5 minus y. And then, of course, I would multiply that through and take its derivative. This is, again, a quadratic. This is going to be 5y minus minus y squared. So we know this is a quadratic. It is opening upside down. So we know we're guaranteed a max. So find all of the rectangles with a fixed area. Which one has a minimum perimeter? Oh, well, this one's different now. My constraining function is the area. So the area cannot change. So I have some area which is going to be equal to x multiplied by y. So we have some area A. That is my constraining function. This one is my constraining function. I still have x and y, and I want to minimize the perimeter. Well, my perimeter, my P, is going to be equal to 2x plus 2y. I'm going to use my constraining function. I'm either going to solve for x or y. I'll solve for y this time, so I have a over x is equal to y. And that will be plugged into this other function, which is my objective function. This is my objective. This is my constraining. And so I'm going to put this in here. I'm going to have P of x now is equal to 2x plus 2, and I have a over x. And then, of course, I would take its derivative. Now, this is not a polynomial. This is not a polynomial. And it's not a quadratic with its upside down shape. So I am not guaranteed a maxima or a minima. So for this one, I probably would consider thinking about looking at the second derivative and plugging in the value, the critical points I got from my first derivative to decide whether or not those critical points actually are a maxima or a minima. Let's take a look at my next example here. I have what two non-negative real numbers, a and b, whose sum is 23, maximizes a squared plus b squared. So a plus b is equal to 23. This is my constraining function. So this is my constraining. And a is the first non-negative number, and it's real. B is a second non-negative real number. This time I didn't write a picture, so I wasn't able to draw a picture, so I have to tell you what I'm using. So I have a and b, I have my constraining function. My objective is going to be the maximizing, so I'm just going to call this f is equal to a squared plus b squared. So now I'm going to take, this is my objective function. I'm going to take my constraining function and either solve for a or b. I'll solve for a this time, so a is equal to 25 minus b. So f of b is going to be my a gets replaced with 25 minus b, the quantity squared. And then I'm going to have b, the quantity squared. And I would then, of course, would do my derivative of that after I multiply this thing out. And then after I do my derivative, I'm going to make a decision about whether or not that is a max or a min. And it depends on what the ending result is. So this is a quadratic. Well, maybe it is and maybe it isn't. I think it is a quadratic. It is a quadratic in which it is opening up. You need to confirm that, multiply that out and do its derivative, and then make sure that you see that the b is going to be the value that is going to either minimize or maximize. Now, here's one that says that Suppose you have an airline policy states that all baggage must be in box shaped with a sum length, width, and height not exceeding 108 inches. So you have this rectangular shape. Okay, so here's this rectangular shape. We have a square-based box, so I'm going to call this X and this X. You can see that's the base, and this is Y. Now, this allows me to say that my length, which is X, plus my width, which is X, plus my height, which is Y, has to be 108. So here's my constraining function. I have two X's plus Y have to be 108 inches. What are the dimensions that is the greatest volume? Well, the volume of this box, so the volume of this box is going to be the X multiplied by the X multiplied by the Y. So my volume is X squared multiplied by Y. I'm going to take this constraining function and solve for Y. Y is equal to 2X, excuse me, it's going to be 108 minus 2X, 108 minus 2X. I'm going to put that in here, and now it's a function. The volume is a function of X. So I have X squared, I have 108 minus 2X. Now, this is not a quadratic. It's going to be a cubic, so if I multiply this through, I'm going to get 108x squared minus 2x cubed, and so I have a cubic function, which means I am guaranteed neither max or mins on the domain that I have. So let's talk about what the domain is, right? So it makes no sense for x to be 0. If x was 0, then I don't have a rectangular box. I've just got a piece of paper or a piece of cardboard. So I know x itself has to be greater than 0, okay? But I also know that x has to be less than twice this 108, right? So I also know that 2x has to be less than 108, because if 2x equaled 108, that would mean that y is 0. And once again, I just have a piece of paper or a piece of cardboard. So the x values at most can be less than 108 divided by 2. So my domain for x, I use interval notation, has to be greater than 0, and it has to be less than 54. Because if it was equal to 0 or if it was equal to 54, then I would just have a piece of paper. Similarly, the thing is going to have to be the domain for y. So y cannot be equal to 0, because if it was equal to 0, then I have a piece of paper. And y has to be less than 108. So those are the constraints that I have on my constraint function to begin with. Now notice that I have no endpoints to check, because my endpoints are non-inclusive, so I don't have to worry about maximas and minimas, absolutes happening on the endpoints. So now I'd go ahead and take this derivative of this function in terms of x, this volume function in terms of x. I'm going to get 2 critical points, and then I'm going to make a decision about those critical points, either based on the second derivative test or doing a sign chart, and then from there going back and answering the question. Okay, let's take a look at my next example. We have 2 poles are connected by a wire that is connected to the ground. The first pole is 20 feet tall. The second pole is 10 feet tall. There is a distance of 30 feet between these 2 poles. Where is it anchored on the ground to minimize the amount of wire needed? All right. So I've got it laid out fairly well, and I know that I've got first this triangle, and then I have this other triangle, and I'm going to make the assumption that the pole and the ground are going to be making right triangles. Now I'm going to call this R1, I'm going to call this R2, and what I'm trying to do is I am trying to minimize the amount of wire needed. The amount of wire needed is going to be R1 plus R2. So I'm going to call this L, which is the length of, L is the length of my wire. Length of wire. Anchoring to the ground. Call these guy wires. Okay, this is going to be R1 plus R2. And this is my function I'm going to and this is the equation I'm going to optimize, so it's my objective function. Now, what I have is this. This is going to be 10 squared plus x squared is equal to R1 squared, because of the fact that I know that is a right triangle. At the same time, I'm going to have 20 squared, and this is going to be squared. And then this length that I have for the second triangle, 20 squared, is going to be 30 minus x. So plus 30 minus x, the quantity squared, is going to be equal to my R2 squared. I now have 3 equations, and I have 3 unknowns. So my first equation is 10 squared plus x squared is equal to R1 squared. My second equation is 20 squared plus 30 minus x, the quantity squared, is equal to R2 squared. But I'm trying to get this length. Now the length is not R squared plus R1 squared plus R2 squared. So I could take the square root of this, and this side, which is the 20 squared plus 30 minus x, the quantity squared, and I could take the 10 squared plus x squared and take the square root of it. And that would give me R1 and R2. So my L would then be, in terms of R1, would be the square root of 10 squared plus x squared. And then my R2 would be the square root of 20 squared plus, and I have 30 minus x, the quantity squared. And that would be my replacement for R2. And now I've got a function in terms of x. So L of x is equal to the square root of 10 squared plus x squared plus the square root of 20 squared plus 30 minus x squared. 30 minus x, the quantity squared. It should be 30 minus x, the quantity squared. 30 minus x, the quantity squared. All right. So I now have it as a function of L. Not excited about taking this derivative. Let's go ahead and do its derivative and see what happens. So L prime of x is going to be, this is going to be 1/2. 1/2. And then it's going to be 100 plus x squared raised to the negative 1/2. And it's going to be multiplied by my inner function, which is, because this is a chain rule, this is going to be 2x. And then the second derivative is going to be 1/2, and I'm going to have 20 squared, so that's 400. Change that to 400. And then I'm going to have plus 2 times, or excuse me, I'm not ready to do the inner function derivative yet. So this is going to be 30 minus x, the quantity squared. This is going to be raised to the negative 1/2. Now I'm ready to do the inner function derivative. And the inner function derivative, 20 squared derivative is 0. But then I have to do the chain rule within that even further. So that's going to be 2. 30 minus x, and then multiply, raised to the power of 1, and then multiply the derivative of x, which is 1. Okay, so what I'm left with is L prime of x is equal to, now I'm going to set this thing equal to 0 and solve, and since I'm setting this thing equal to 0 and solve, I'm going to multiply everything by, let me see. Well, before I even do that, let's talk about what cancels. This 1/2 and this 2 cancel. This 1/2 and that 2 cancels. So what I'm left with is x over 100 plus x squared, the square root of it. And then I'm left with plus 30 minus x over the square root of 400 plus 30 minus x, the quantity squared. If I set that equal to 0. If I multiply everything by the square root of 100 plus x and the square root of 400 plus 30 minus x, the quantity squared. I'm going to get x, the square root of 400, plus 30 minus x, the quantity squared, plus 30 minus x multiplied by the square root of 100 plus x squared is equal to 0. Let's move this to the other side of the equal sign. So I have x, the square root of 400 plus 30 minus x, the quantity squared. And then on the other side, I'm going to have, well, when I bring this 30 minus x to the other side, it'll be a negative 30 plus x because the signs will change. So I'm going to do x minus 30 multiplied by the square root of 100 plus x squared. And then I'm going to go ahead and square both sides to get rid of square roots. And so I'm going to have x squared multiplied by 400 plus 30 minus x, the quantity squared. And then on the other side, I'm going to have x minus 30 multiplied by 100 plus x squared. And then from there, I'll let you finish that off because then it's just a matter of distributing and setting equal to 0. You're going to have a power of 4, so it's hopefully reducible to a quadratic. If not, then you're going to have to use the skills that you learned in your pre-calculus 1 class to figure out where your critical points are. Okay, we have a rectangle beneath a semicircle. The rectangle is constructed with its base on the diameter of the semicircle with a radius of 5 centimeters. With 2 vertices on the semicircle, what are the dimensions of the rectangle with maximum area? Okay, so I'm going to put this on the xy plane. I have a rectangle beneath a semicircle. So here's my semicircle. I have a rectangle that's constructed with its base on the diameter of the semicircle, and I have 2 vertices. Okay, so here's an example of what's happening. This is the x-axis, this is the y-axis. Let me see. The radius is 5 centimeters, so we know that this equation, which is the semicircle, is going to be x squared plus y squared is equal to 5 squared. Solving for just y or x, and I'm going to take only the positive, I'm going to have y is equal to the square root of 25 minus x squared. So that is the equation of the semicircle. What is the equation of the rectangle? Well, if this is x and this is y, then my equation for the, let me see, what am I trying to do? The maximum area of the rectangle. So if that's x and that's y, then this is an additional x. So I have 2x for my area of the rectangle is going to be 2x multiplied by y. I'm maximizing the rectangle. So this is my constraining function, and this is my objective function. So I'm going to put this square root of 25 minus x squared into here, and then I'm going to take its derivative. And I'll let you all finish that. Okay, so let's take a look at the next example. Imagine a flat bottom cylinder pot with a circular cross section of a radius of 4. A marble with a radius of 4 is placed in the bottom of the pot. What is the radius of the marble that requires the most of the water to cover it completely? Okay, so I have a flat bottom cylindrical pot with a circular cross section of radius of 4 inches. So I have this cylinder that looks like that. Looks something like that. I have a marble whose radius is between 0 and 4 is placed in the bottom of the pot. So I have this circle, this marble that's going to be placed in there. We have this radius here. My radius is going to be less than 4, but obviously bigger than 1. What is the radius of the marble that requires most water to cover it completely? Oh, well, that's interesting. Okay, so we have the volume of the cylinder. So the volume of the cylinder is going to be, let me see, do we have a radius of 4 inches? Do we have a height of the water? Nope. So the volume of the cylinder is going to be pi r squared h, where h is the height of the cylinder. We have the volume of the marble, and this is 4/3 pi r cubed, I think. I'm gonna have to go find that. Yes, it is. I just checked. Okay, so then the volume of the water is going to be the volume of the cylinder minus the volume of the marble. So the volume of the water is going to be pi r squared h minus 4/3 pi r cubed. Now, we have two different r's, so we're going to call this R1, and that comes from the cylinder, and then we're going to have R2, and that comes from the marble. So I need to have R1 is from the cylinder, and R2 is from the marble. Now, we want the one that requires the radius of the marble that requires the most water to cover it completely. So we've got to decide what is it that we are trying to maximize. Well, in this case, we're trying to maximize the volume of the water, which is the volume of the cylinder minus the volume of the marble. Now, we do know the volume of the cylinder, so we can actually replace it. That's 4. They told us that was 4, so I don't have to even do the R1, R2 stuff, so let's replace that with the 4. So here's my 4 squared, and then I'm going to go ahead and replace it here with the 4. So that will be 4 squared. The height, well, we don't know what the height is, but the height of the water is going to be the height of your marble, right? Because if this is the radius of the marble going straight down, and then this is the radius of the marble going straight up, so the height that I'm going to fill this to is going to be twice whatever my radius is for my marble. So I can replace my h as well. So I can replace my h with 2 times my r2. So 2 times r2. So 2r sub 2. Well, now I only have one variable, so the volume of my water is only in terms of R2, and I can just call it R at this point. And it's going to be equal to 16 times 2 is 32 pi multiplied by R sub 2 minus 4/3 pi R2 cubed. Then all I have to do is find my critical points there and decide which part is going to be the one that I will use, because I will end up with 2 critical points, and I will decide whether or not both of them make sense. If they both make sense, then I have to make a decision whether or not which one maximizes and which one minimizes. Okay, we have a rectangle is constructed on one side of the positive x-axis, one side on the positive y-axis, and it is on the vertexes on that. So this is my constraining function. My function I want to optimize will be the maximizing the area. So we know this is x, this is y, so my area is going to be x multiplied by y. I'm going to use that and into the function I want to optimize. So once again, we're going to get something like a is equal to x, 10 minus 2x. Distribute through, find the derivative, and that will help me decide what my dimensions are. And that's it for this video. This shouldn't be on the notes. It's not on this video. And that's it. Nice, short-ish video compared to some of the other stuff, and we will see you in class. Bring questions.